What I thought we'd just do quickly is show a game. I've got these cards, I mean you'll have to print them off up on Ottle, and it is one way to help you learn all these different reactions that you need to know off by heart. So I call it organomy because I'm rhyming it with rummy. Has anybody here played rummy? No? I'm obviously showing my age. Rummy Cub is a variation of it, and I know there is that game out. But really, basically, what we've got is you have 7 cards that gets dealt out to each person, and then you have a deck where you take cards off, and you've got a discard pile where you throw away the cards. And the aim is for you to get rid of all the cards in your hand. And the only way you can do it is by putting down sets of 3 or more. So in this organomy version is to use a reactant, a reagent, and the product. That's your set of 3. So based just on these alkene reactions that we've got here, I'm doing it now so you can learn these before you add on the next lot to learn and the next lot to learn. So variations are you can add to the set of 3 already formed, and you have to of course finish by discarding a card. So you start by picking up a card and discard it, and the first player, as I said, who gets rid of all their card wins. So here's an example. Now normally of course your deck, you wouldn't actually see what's in the card. I mean, if you play card games, normally the deck you just see the picture at the back. I'm just showing you what it is because it's just easier. So player A has been given 7 cards, and so has player B, and they have to try and get rid of their cards. So player A picks up a card to start his turn, and he has a look. Now based on what pardon me, based on what you learned from last week, can you put together a reaction where you've got a reactant, the reagent? So the reactant is one of these with picture of so he's only got 2 over here, a reactant, a reagent, so that are these cards with arrows on, or a product, and again they have to be one of these. Can he make, or she makes, a set of 3? Okay, let's have a go. What he has got is an alkene, and he can form an alcohol by using this reagent. So he can put those down, and not only that, do you remember whenever we add to an alkene and we've got an asymmetric one, we use Markovnikov's rule. Do you remember that? Okay, you do. Great. Now Markovnikov's rule, for those that don't, is, remember, you just can remember it as the rich get richer. But remember, don't use that in the exam. The proper definition is the hydrogen atom adds to the carbon atom that has the most number of hydrogens. So here's my asymmetric alkene. It's not the same because I've got a hydrogen there and an alkyl group there, so it's not the same. So this carbon over here has got more hydrogens. It's got 2 than that carbon, which has only got 1. So the incoming hydrogen will add to the carbon with more hydrogen atoms, and that is the major product. So player A can also get rid of that card as well. So it's now he has to throw something away. He just picks any one of his reagents, so he's got 3 left now, and it's player B's turn. So now it's player B ready to go. So he picks up a card, and if you have a look, there's actually nothing here, because remember, this set of cards, we're just dealing with the alkene, so you have to have an alkene in your hand, and he actually doesn't have any alkenes. So he's just got to get rid of a card, and he just happens to choose that one. Now it's player A's turn again. He's only got 3. He picks up a card. He's now got a product there, but so he's got to get rid of a card, so he just does that. Now it's player B's turn. Player B picks up a card. It's still not an alkene, so they can't do anything. So he decides to just get rid of it. Player A's turn again, picks up a card, a reagent, has to get rid of it. Player B's turn, now he's finally picked up an alkene. Can he put something together? So can you make a reaction with an alkene going to any one of these products with these two reagents? Would anybody like to have a go as a yes or a no? Do you think there is a set of 3 there? Correct, there isn't a set of 3 because the bromine will add 2 BRs onto it, and that's a Cl anyway, so it can't be that. And this is an oxidation where we add 2 OHs, so you can't form that because that's only had 1 OH in. So player B still can't do anything, so gets rid of a card. Okay, that should have gone on top, but anyway. Now it's player A's turn again, picks up a card, and yay, he's got now something. But again, he doesn't have an alkene, so he hasn't got a reagent to start it off, and so he decides to throw away that one. Player B's turn, picks up a card. Can you see player B can do something now? Because, well, strictly speaking, yeah, there's an R group over there. So if he has an alkene and reacts it with hydrogen over a catalyst, he can form an alkane. And there's no major or minor product associated with that, so he can't use that. And so he just throws away a card. Now it's player A's turn, and we'll just go very quickly. He's got an alkene, and he can now put something together, and he can throw away a card, which means he's got no cards left, so he's won. Player B, if player B was now going for it and added another card, actually he can, because he can build on a pack that's already there, he can add that, and that's a minor product, because can you see the hydrogen has added onto this carbon and not to that one? Is that clear? And then he could also say, right, my alkene can form the bromine to get to this reaction, and he can throw away a card. So it's up, let me go back. So it's up to you whether you decide whether he's also won or not, seeing he started second. But do you think that game would help you remember, or is it just too difficult to remember in the first place? Anyway, the cards are there if you want to print them out and have a go. I suggest you always, make enough copies and do just a set at a time. So just do the alkenes and then just do the alcohols, and when you've got those reactions fixed in your mind, then start putting them together so that you can go from an alkene to an alcohol to an alkyl halide and so on. Okay, right. Now, that's a very dense slide. But those are all the reactions you need to know. So remember I said one of the tips was think of the type of reaction that you're doing. Is it an addition? Is it a substitution? Is it an oxidation? Is it an elimination? Or is it an acid-base? Now we've done a fair amount of that already last week. So if you think about it, that blue we've all done. So we've done addition of alkenes. This, remember, is the hydrogenation. What do we call it when we add a halogen like chlorine and bromine? Does anybody want to have a go? Remember, there were those 4 reactions starting with H. Hydrogenation, hydration, halogenation, and hydrohalogenation. Does anybody want to have a go? No? Okay, Nicholas is having a go. So just think of it, we are adding, yes, halogenation. We are adding a halogen, either Cl2 or Br2, so either 2 Cls being added on or 2 Brs being added on. So it's halogenation. This, remember, we're adding water, so it's hydration. Now you may either see it as H2OH+, saying water with an acid, or you may see it, and this is a better form because you have to actually say you got conc acid. So concentrated sulfuric acid and water. So what's given in brackets is actually the better version. And then hydrohalogenation is when you're adding HBr, HCl, that sort of thing. And of course, remember we did Markovnikov's rule with the major and minor products. The only one we haven't done yet, and I'll do that I think towards the end, is polymerization to make polymers. Okay, so you need to be able to do that if you're going to do the CH2000 standard on polymers, because you have to explain your understanding of polymerization. Right, we've also done a bit of elimination in that we've learnt about the rule. Do you remember what the rule was for elimination reactions? If it's if it was Markovnikov for addition, what is it for elimination? And there was a bit of a duh moment for me, wasn't it? So Nicholas, I see, is typing. The poor get poorer. At least you sort of explained the quick route. It's Zaitsev's, and you need to be able to, name the rule, and then say, of course, you can remember there's the poor get poorer, because if you're getting poorer, you're losing something, so you know it's linked to elimination, and so it's the hydrogen gets removed from the carbon atom that has the most number of hydrogens. Okay, so we're going to carry on, and we're going to look at first the hydrogen halides, so the haloalkanes, and then we'll do the alcohols and so on. So haloalkanes, remember with that tip of how would they react? Halogens tend to be quite electronegative, particularly fluorine. Chlorine also is quite strongly electronegative. Bromine and iodine not quite as much. But it means that the carbon is a bit more positive. So you're going to attract something negative to it. So if you're trying to work out your reagent, a hydroxide of some sort, if you want to form an alcohol, is a good idea. Okay, so what I'm trying to show here is the hydroxide adding on and the chloride coming off. So nucleophile, this is a term you learn at level 3. You won't have to use it at level 2, but it's good to get that idea in your mind now. Nucleophile is something that loves something that's positive. Nuclear positive, phile loving. So positive loving, and it's positive loving because it's negative itself. And so it'll add on and kick off the chloride, the bromide. I've got myself confused with my halides there. That should have been, say, the chloride. And you are then left with an alcohol. So it's a substitution reaction because I'm removing the halide and I'm replacing it or substituting it with an OH. Okay. I can, though, also, if I've put in strong, severe conditions, I can push for an elimination. So have a look at the two different reagents. They both OH minus hydroxide because they're attracting something that's positive. They're attracted to a positive, which the halogen is, the carbon attached to the halogen is. But what is different between a substitution reaction reagent and an elimination reagent? Have a good look between those. What is different? Shania is typing. Anybody else would like to have a go? Okay, the form that the OH is in, yep, and it's a solution. AQ means it is in water. Okay? ALC means it's alcoholic. So there's no water present here. Okay, the reason is water contains H plus ions and OH minus ions. So If I'm having it in a solution with water and I've got hydroxide in it, doesn't matter if I've got other hydroxides in it as well, because my OH is adding on. With elimination, I don't want the OH to add on. I want the OH to remove something. So if I've got, OHs from water coming around, then I'm going to form the alcohol and not the alkene that I want. And to drive that, to get the energy, I have to heat it. Because what happens here, I now have to remove a much stronger bond, or break a much stronger bond. The CH bond, if you think of your bonding energies that you did in the 2.4 standard, who's finished the 2044 booklet? Anybody? Nobody? Okay, you have. Do you remember the bit about bonding energy? Now, you won't have to ever learn those things off by heart because they'll always be given to you. But next time you have a look, notice how strong the CH bond is actually. So you need more energy to break this bond than you do to break that bond, the CBr bond. So that's why we have to heat it. We have to force it to make the OH go and take this hydrogen off instead of just adding on. Okay, so what happens? The electrons from there move to form the double bond. The Br still has to come off, but so our leaving group is still the Br minus, but we've also got water coming off, because remember, it's an elimination, so we're not just replacing, we're taking away. So we've taken away the Br minus, and we've also formed water to form the alkene. Okay, and here of course it is a terminal alkene because my Br was on the end carbon. So I can only form one type of compound. Okay, so are you clear about the two different types of reagents and why we use them? You won't have to explain why we use them in an exam, but it's a way of remembering. If you understand why you use it, you'll remember it better. Okay, and then do notice the reaction conditions because that is important. Now here this is just simply a elimination reaction. Look for YouTube MAT and that will help you find it, because it's 3 minutes and I don't want to go 3 minutes through this. But pretty much when you look at these reagents, ask yourself questions to see if you've understood what is happening. So I've said, asked here, why is the reactant a liquid? Because do you notice he's pouring in a liquid? Okay, but the product is a gas. So think of your intermolecular forces, because it's your intermolecular forces that is determining the boiling point. So my do you think this is a polar or a non-polar compound? 2-chloro-2-methylpropane. Okay, can you see that the molecule would be asymmetric, so the bond dipoles won't cancel out, so this would be polar. Not strongly polar, but it's polar enough, and it's quite also a heavy molecule, so the forces of attraction are stronger, meaning that this is going to be a liquid. But if these are the compound. If I remove, because remember it's an elimination reaction, and you can see there's the product, the gas being formed. If I'm removing a Cl, so I'm trying to find my cursor there. If I'm removing a Cl and a hydrogen, what am I going to be left with? What sort of functional group? So remember, elimination always leads to what type of compound? If you go back to that previous slide, what did we form? Does anybody remember? Okay, so I'm going to go back. When we had an elimination reaction, what type of functional group did we form here? Does anybody know what this is? It's an alkene. Correct. Okay, so is this polar or non-polar? So alkenes are always tend to be considered non-polar. Okay. If it's non-polar, do you think the forces of attraction between the molecules are strong? So straight yes or no answer. They aren't strong, correct. So do you think it will have a low boiling point or a high boiling point if there are only weak attractive forces between the molecules? A low boiling point. And that's why when I go here, and I'm just going to drag this on as we go, that's why we start off with a liquid, but we actually finish up with a gas. Okay. And then at the very end, what he does, do you remember the test for an alkene when we add bromine water? Okay, so he's adding the bromine water there. I don't know if you saw it was a bit yellow, and as he shakes it, it should go a little, it's pretty much not yellow anymore. There, can you see it's pretty much colorless. So remember that test for an alkene, the alkene decolorizes bromine because it adds on. Then the final thing is he just simply lights it, and that's to show, you know, it's a hydrocarbon, it burns easily, because haloalkanes don't burn. Okay, right. So reactions of haloalkanes, we've done the elimination where we use alcoholic OH minus, so it's concentrated, we heat it, so we give it strong, severe conditions to eliminate something. Add lots of energy to drag off that hydrogen. We've also got two substitution reactions that you have to know, which is using ammonia to form an amine or using OH minus to form the alcohol that we've already come across. So you have to know 4 reactions for the alkenes plus polymerization and the tests. For the haloalkanes, you need to know 3 reactions. Okay. And we always form primary amines. Okay, sorry, and that forms alcohols. And that forms alkenes. Okay, so have a go with this. Which one of these, 1, 2, or 3, is going to form alcohols? Number 2. Form alcohols? No, not number 2, because number 2 is alcoholic. So it won't be number 2, but you are correct, it is OH minus, so there's only one other one to do. Number 3. Okay, right. So that's to form an alcohol, and just think of aqueous with it. Think of alcohols dissolve in water as a tip sort of thing. It's got really nothing to do with it, but it's just to help you remember alcohols, water. Alkenes don't dissolve in water, so you don't put them in water, just as a memory aid. Formation of primary amines. Which one of 1 and 2 do I use? Number 1, correct. Okay, and obviously then to make an alkene, I have to have alcoholic OH. You can say concentrated OH minus alcoholic, or OH minus alcoholic with heat. You know, that's the bare minimum you can write down. Now, as you know, I've explained why we used alcoholic OH minus to form the alkene and not the aqueous. But why? Because an amine is a base. Okay, so why can't we use aqueous ammonia? Why does it have to be concentrated and dissolved in an alcohol? Why can't we use aqueous ammonia? And This is dealt with in more detail when you go to the next exam standard, the 2.6 standard. The lovely thing about chemistry is the more chemistry you know, the easier it becomes, because it's like a jigsaw puzzle, everything fitting in. Okay, so if you think of it, if I take ammonia and dissolve it in water, then the ammonia is a base, so it will take off a hydrogen from the water to form ammonium, and then of course H2O minus or H plus is going to be left with OH minus. What happens if I have OH minus in water around? Look at these reagents. What am I going to form if I've got OH minus? Aqueous OH water, we're going to form some aqueous OH minus, and I hope you can see from that, if we use aqueous ammonia to make an amine, we're actually not going to land up making an amine, we're going to make an alcohol, or we'd make a mixture, probably just a mixture of it. So that's why we use the alcoholic or the concentrated version of ammonia. Okay, right, and then that was if we're using an amine. Sorry, that's from level 3. I've just adapted my level 3 slides for my level 2. So we've done the haloalkanes. There were those 3 reactions. The alkenes, so it's an elimination to form an alkene, and then the 2 substitution reactions. So now let's look at the next one, which is the alcohols. So we've got substitution reactions for alcohols, and we also have elimination, and we have oxidation. So let's have a look. Again, we've got a carbon attached to an electronegative oxygen, so the carbon is quite positive. So I'm going to need some sort of negative nucleophile. So, for example, to make a haloalkane, there are a number of options you can use. So it's the SOCl2, which is thionyl chloride is the name, is a good one to remember. So if you're going to try and make a haloalkane, well, a chloroalkane, remember to use thionyl chloride. It's the best one to use because it's a gas, it's clean, it gives you good products. So that will kick out the OH minus, it's a leading group, and the products that you get from this and that is HCl, well, you get OH minus and you get HCl and SO2 coming off. So those are gases that can be easily removed from the reaction mixture, so you're left with quite a clean product. If you use any of the others, you get lots of mucky stuff that you've got to sort out. And so you have added now a chlorine group. So I've changed from an alcohol and I've replaced the OH minus with the Cl2. So that's a straightforward substitution. There are, as I say, 4 ways you can change from an alcohol to a haloalkane. The SOCl2, the thionyl chloride, is the best one. You can learn the PCl3 and PCl5. Those are also given, but they actually are very mucky. And then the other one is HCl, which I would strongly recommend that you don't use. I know the standard says HCl, you know, hydrogen halides, but I think that's because they wanted the HBr, because in real life HCl really doesn't work well at all. Okay, so I've said there, avoid using HCl for substitution reactions. It won't necessarily get marked down because it is in the standard, but practically it's not a good thing to use. Okay, so only use HCl when you make a haloalkane from an alkene and not from an alcohol. So here are some examples. So if you just look at for Frankly Chemistry on YouTube or Nile Red, so here they, let me just, so this is a long video, so it's 26 minutes, but notice they explain the whole thing. Now they do use, after what I've said there, conc HCl, so that it can be used, but it's not the standard form. And actually, we can use it just because we've got a tertiary haloalkane there. And then we've got here another one where they use HBr. And what's interesting about this one is the way they actually make HBr in the mixture. So if I just move it on to about 1 minute. So that sodium bromide and the conc H2SO4 is they first make the HBr and then they react it. So that's just for interest. I think it's a good thing to sort of see what happens because you can't actually do this in the lab. So it's good to see how things are done. So have a look at those videos. Okay, here is some more. This is reacting ethanol with thionyl chloride. So that was the reaction. And so they're showing the liquid, okay, thionyl chloride. It's very low boiling, so it is there as a liquid, but it comes off all as gaseous. And in other words, the products are gaseous. Sorry, I'm not very clear there. Can you see how it's fuming away there? So it's reacting with the water and the air, and that's why it's fuming. While that's going, here they're using PCl5. Notice PCl5 is actually a solid. It makes sort of a clumpy thing. Now this notice is to test for the presence of OH minus groups because there is a reaction, but it just by if you just have a look, you'll see what happens. It starts bubbling because, well, just drag it on. Can you see that there's a gas coming off? That's acidic. Okay, so again, you have a look later on yourself, and then you can see what's happening there. Again, he's testing for the gas, the HCl gas that's coming off. So he's using ammonia here, and that fuming there shows what's happening. The permanganate is to test for the SO2 gas coming off, because SO2, if you've done the redox, if you've done 2.7 already, SO2 is a good reductant, permanganate is a good oxidant, and can you see it goes colorless? So that's good redox chemistry being used here in organic chemistry. Any questions? Has anybody actually gone through and looked up these YouTube clips that I've indicated here? Or, I mean, if you haven't, you have, okay. So you can find them easily. Because if you can't find them easily, then let me know. And because I haven't always kept things up to date. Okay, so there he's also testing for things. Right, let's carry on. So we've done a substitution, changing an alcohol to a haloalkane. Now we're going to do elimination. So remember the Sisyphus rule. The poor get poorer. In other words, the hydrogen of the carbon of the adjacent carbon atom. So that one doesn't count. It's got to be a carbon atom that's adjacent to the carbon that has the hydroxyl. So which one of these two have got more hydrogens? This one's got more hydrogens. This one's got fewer hydrogens. So one of these hydrogens are going to leave, making the double bond form between these two carbons. So that's where it's going to go. Notice the heat, because I'm breaking that CH bond again, and I form, can you see I can form geometric isomers for this particular example. Is this a cis isomer or is it a trans isomer? Trans. So always whenever writing something down, particularly if you're going for excellence, and I hope all of you are pushing yourself to do as well as you can, always ask yourself, if I draw it like this, it's trans, do we have geometric isomers, and so on. And then you can just put more information down, because of course you can form the trans and the cis as well. And if you did it over here, then you can see I've drawn the trans over there. So a yellow hydrogen is gone rather than a blue because of the site-Ceph rule. Okay, and here is again, and this is a 3-minute long video, and what they're doing is they're using a cyclo compound, which you don't have to know about, but you'll see it's to make an alkene. So they explain the whole thing as well, so it's you can see what they do. So you should see heating, because remember we said it's heat, and you should see that they're using some sort of strong concentrated form of something, if you listen to it, just to make it go to an elimination reaction. Okay, then the last one, so we've done one substitution, which is the alcohols to the haloalkanes. We've done one elimination, which is the alcohols to the alkenes. And now we're doing one oxidation reaction. So the alcohols, as far as you're concerned, are also 3 reactions, but they're all 3 different types. And that is when I make them undergo oxidation. Now, for organic chemistry, if something is oxidized, how do we recognize it? I mean, I know we should look at oxidation numbers, and we should look to see if electrons have been lost or gained, or lost for oxidation, but it can be quite tricky working out oxidation numbers for organic compounds. So, because different carbons will have different oxidation numbers. How can I easily see if something's been oxidized for organic chemistry? Anybody want to have a go? The clue is sort of in the name, oxidation. So what element do you think of when you hear the word oxidation? So a few of you are typing. The presence of oxygen, yep. So please don't say this rule for when you do redox in the 2.7 standard, because there we only give you stuff where you can work out the oxidation numbers properly. But for organic, you can, if you're either adding oxygen or removing hydrogen, you've oxidized it. So here I've got one oxygen, okay, and that carbon that has the OH group also has one hydrogen attached to it. Now, remember what I said, oxidation is the addition of oxygen or the removal of hydrogen. It's that hydrogen that's going to be removed that's important. So if that carbon did not have a hydrogen, so in other words, if this was a CH3 group as well, you couldn't oxidize it. But because I do have a hydrogen there, it can be oxidized. And a good oxidant is always, if you've done redox chemistry, is acidified permanganate or acidified dichromate. Acidified permanganate is purple, going to colorless for the Mn2 plus ion. Acidified dichromate is orange, going to the green Cr3 plus ion. So you can also use those as tests. You know, if you see a color change, you know that you've oxidized something. So that, sorry, I had to add in those double bonds there because my program didn't show a double bond. So I've formed, I've suddenly just realized you don't know this functional group. This is an alkene. So let me go, ignore that bit. This is, sorry, that's level 3. You learn that at level 3. This, can you see, I've got 2 hydrogens that can be removed. So I can first remove one hydrogen, and again that compound you will learn about next year. And this is the one you are going to have to know, is if I take my alcohol, and forget this step, if I reflux it with dichromate or permanganate, either or, it doesn't matter, I get the carboxylic acid. So I can oxidize a primary alcohol to the carboxylic acid. Because I've got two hydrogens, it gets done in two steps, but this is the end point, the carboxylic acid. So remember that a primary alcohol is the only type that can be oxidized to carboxylic acid. So if you get given, what is this, a primary, secondary, or tertiary alcohol? The definition, remember, of primary, secondary, tertiary is you look at the carbon to which the group, functional group, has been attached and say, is that carbon attached to one other carbon? If it is, it's primary. Two other carbons, if it is, it's secondary. Three other carbons, it's tertiary. So what is this carbon? Is it attached to one, two, or three other carbons? Secondary, because it's attached to two other carbons. Correct. So that, can I form a carboxylic acid from a secondary alcohol? No, because I don't have that second hydrogen to remove, so it's only primary. Okay, so that is the last of those, and of course tertiary won't get oxidized at all. Okay, so that, we should have time to go through the amines, so let's have a go at the amines. The amines, you only have to know the amines in terms of acting as a base. And sorry, I haven't, let me just have a quick look. Yep, so this is acting as a base. Can you see what's happened here with the nitrogen? It had a lone pair of electrons and it accepted a proton to form this cation. Okay, so that is what a base is. Remember, a base accepts protons to form the conjugate acid. So can you see it's added, an H plus has been added on. So the main thing you need to know about amines is that it is a base, so it'll accept protons. I can react it with any acid, HCl, H2SO4, nitric acid, any acid, as well as, of course, as the organic acids. So like ethanoic acid, methanoic acid, and so on. So that is, if you think of those reactions we looked at right at the beginning, those acid-base reactions at the end. Okay, now if you wanted to know the name of that, you could either call this a ethyl for two carbons, ethyl ammonium ion, because that sort of comes from that, obviously can't be NH4 for ammonium because we've got one bond going to here, or you can also call it the ethanaminium ion. This is the newer version, that's the old version. And there's only one M in there and there's two M's in there if you're concentrating on the spelling. Okay, so that's really the only one you have to know about the amines. And so that's where we finished. What I want to do, so I'll just leave that slide there. What I'll do next week, because I was getting a bit behind getting this ready, is look at the reactions of carboxylic acids. And really we've done it all already. We're just going to show carboxylic acids reacting with the amines and making carboxylic acids from the alcohols, which we've already done, and then polymerization. And then we'll just look at reaction schemes of how to change from one to the other to the other. Any questions?